Welcome back to the Art of Math. Today we are going to go over fractals. This video will be on why I love fractals. Now, the love part of it will be at the end, so that's not meant to be a clickbait title or anything. I just want to build up to this so that you guys can appreciate this more. So for now, I just put this in there as a hint, the yin-yang symbol. That kind of has to do with it. So maybe you want to think about how that might be connected if you already know something about fractals. So let's jump right in. So how to best use this video. This video won't, as with the previous videos, this video won't be the definitive treatment on fractals. I want to give you guys a high-level overview, and the main goal is so that basically you get to just explore the topic mainly on your own. So after this video, hopefully one or two things will jump out at you, or at least after looking into the many links in the resources section or the description of the video, you might get interested in something. As Richard Feynman, I believe, used to say, I don't want to deprive you of the joy of learning and figuring things out for yourself, or for yourselves. So I don't want to hand feed you everything there is about fractals, nor could I, but I just want to help foster, spark your independent exploration and hopefully make them more fruitful. So I make sure after this video, I strongly recommend you guys look through the links in the resource section, in the description to the video, because that's really where a lot of your, I hope a lot of your further explorations can get going. Alright, so I want to first relate this video to all the previous videos in this series on math and nature and art, specifically 3 videos. So the Exploring Infinity videos, part 5, where we discuss 2D shapes versus 1D shapes and which one has more points, so the number of points. And we had this strange surprise where although a shape was in 1D, it had the same number of points. So that might lead you to think about, can you have a fractional number of dimensions in between 1D and 2D, since these are kind of blended? And that's very much at the heart of fractals. And so in fact, fractals get their shape from fractional. So fractal, dimension, fractional, that all has to do with where fractal comes from. So we'll get into that in a second a little more. So Fibonacci numbers in the golden ratio video, where we discussed, and basically like how does this relate to fractals? They both appear a ton in nature. There's the concept of self-similarity, which we'll discuss in a bit. And there's the recursive definition, so which relates to the self-similarity. So for Fibonacci numbers, we define the nth term as the sum of the 2 previous ones. And similarly, for many fractals, you can define the next part of it as being similar to what happened before. All right, and again, the Nautilus shell isn't a perfect example, but it sort of is used, even though it's an imperfect example. All right, and then the chaos theory video. So we saw, or at least hopefully you guys looked at some of the links in the description and saw that for cellular automata, which is one example that demonstrates chaos theory, you can have just a few simple rules that can lead to very complex and beautiful or chaotic behavior. So fractals can exhibit chaotic behavior, and basically both chaos theory and fractals, some parts of that can just be made of a few simple rules. So that's another connection that I wanted to make to those 3 videos. All right, so that's, and you might want to go and refer to these 3 videos and just see them after this video again to, you might make a little more sense that way. All right, so what are they? What are they? That's a very good question. So there's a disagreement, I would say, as to the precise definition of a fractal. Benoit Mandelbrot introduced the term fractal in 1975, though many aspects of fractals had been studied earlier, certainly in the 1800s, for example, with the mathematician Weierstrass. So, but for our purposes, there's this great video which I really strongly want to recommend and refer you guys to by username is 3blue1brown, and in it basically goes over what a fractional dimension is. So fractal dimensions, fractional dimensions, and I'm actually making a purposeful decision not to cover that in this video, so because I think that video does a great job. And so maybe you want to pause this video, go watch the video which you can find in the description to this video by 3blue1brown, and then come back and resume this video, and then you'll have an understanding of what this is. So And just maybe before you watch that, a little bit of a background, there's many ways to measure the dimension of something, like 1D, 2D, 3D. Most of you guys are probably familiar with the topological definition, and that's your sort of common sense. A cube is 3D and area is 2D. But then when it comes to fractional dimensions, you might find one of these two, which is the Hausdorff or the box counting dimension. And in the video by 3 Blue 1 Brown, he uses box counting, which is usually when you see it explained in like little examples, they'll be using box counting. That involves boxes or cubes. This usually involves spheres. So that's just a little bit of a background. All right. So, and in that video, he mentions this sort of working definition, which I'd like to use, which is shapes with a non-integer dimension. Now that can be very strange. So like I said, you should probably watch that video and then come back to this so you can understand what that means, because I won't explain it here. But roughly, if you have, let's say, 1.4 dimensional shape, that 1.4 part is a measure of the roughness or the jaggediness. So if a shape is perfectly smooth, it's probably not a fractal. All right. Now, as you're watching that, or maybe as you're returning from that video, a motivating question is, how long is the coast of Britain, Great Britain? You could pick another country, India, US, you know, whatever country you want. And you might have an answer, you might have a ballpark number, maybe like 50,000 kilometers, 100,000 miles, whatever. And that might be correct, yes or no. So the point I want to make is it depends on your measuring stick. So if you're measuring it in meters, inches, miles, and I don't mean that in a trivial way as in the number will change as a function of unit. I mean in the sense that the actual coastline will be jaggedy. So if you're using a meter stick, you can't measure all of those, you know, kinks. So that's what I mean by, as you make your unit of measurement smaller and smaller, you'll find that the perimeter keeps increasing. How large can it get? In theory, at least in like mathematical theory, infinite. So that's just something to think about, and again, go and watch that video. So, okay, B. Another definition or strong aspect of fractals is that they are continuous everywhere, but nowhere differentiable. So that sounds like a mouthful, so let me explain what that means. Continuous, but nowhere differentiable. So for continuous, think of it as connected. So if we were to draw like some sort of shape, it just means I never raise my hand. So I don't go draw, pick up my hand, then draw again. So it's connected. So for example, this shape is connected. If we plot y equals the absolute value of x, it's connected everywhere, but it has this little kink. So that gets into the concept of differentiable. So for those of you, I'm assuming most of you have not studied calculus, so there you'll learn the technical definition, but basically just means there's a slope. So if you look at this smooth line here on this left portion, it has a certain steepness. If you put it here, there's also a certain steepness at this kink. It's kind of like a seesaw. We don't really know what the steepness is, so it's not defined. So anytime you have a point, like a sharp point, where it suddenly it's not smooth, then it's not differentiable. So basically what this is saying is that a fractal, think of this as this infinitely intricate, jaggedy thing that is connected everywhere, yet, for example, like this appears smooth right here, the way I've drawn it, this first little bit, but actually if you were to zoom in on that, you will find that that itself expands into more jaggediness. So that's what I mean by, if you zoom into any little portion, it is between any 2 points, it's not going to be smooth anywhere. So that's very counterintuitive, and you might think, how is that possible? Well, a perfect fractal, that's a property of it. So it's a very weird thing, and Weierstrass, the mathematician, is known to have studied that as well in the 1800s. All right, so I'll leave you guys with that. Next, another concept, property, definition, whatever you want to refer to it as, and I want to make a point, like I said, there's some disagreement as to what we should define fractals as. So part A, this is probably the most accepted, saying it has a non-integer dimension, and then this is specified in a technical way, let's say using the Hausdorff dimension. But self-similarity is a common feature. This might be not of all fractals, but maybe man-made fractals or mathematical fractals. but it's still cool. So this hopefully give you guys, and I've been talking a lot, but hopefully this gives you guys an example. So many of you might have seen this. This is called Sierpinski's triangle, or the Sierpinski gasket. You take an equilateral triangle, or just any triangle, you cut it in half by this upside down triangle, so then that makes these three medium-sized triangles. And so we could take this, let's say, top one, and keep doing the same thing with these like even smaller medium triangles, and then do it again and again, and we can do this process infinitely. What point am I trying to make? If we zoom in on, let's say, this one right here, this top medium-sized triangle, and that's all you saw, but let's say I zoom in so it's twice as large, then you won't know the difference between looking at this or the original. Now clearly in my diagram you will, because it's not infinitely intricate, so that you'll say that, oh, this one only has these three, but like the big one has a ton more. But if you do it infinitely, there'll be no difference. So that's what I mean by self-similarity. If you zoom into a part of it, well, actually technically self-similarity might be approximately similar, whereas a stricter version of this would be scale invariance, where it's actually exactly the same. So this is not just self-similar, this is scale invariant, because it's completely identical. It's not just approximately similar. And also another term for this might be, you might come across as expanding or evolving symmetry, which sounds pretty cool. All right, so that's what they are. And again, check out the resource links to learn a lot more. So let's go into where they happen. So where do they occur? So basically, let me move this down. Fractals are everywhere. We humans are made of fractals. The entire universe can be thought of as one giant fractal. I'm going to talk more about this at the end of the video, but that's going to get into why I love them so much. So for now, just list kind of like your generic examples. So yeah, they're everywhere. They're in humans, the universe, nature. I mean, like in terms of big concepts, these underlying ones are the field. So they come up in nature, in art, in mathematics. You can see the artist Escher's work. He uses a lot of fascinating fractals. Video games. So if you guys are gamers, or you know, like if you really like video games, I'll talk a little more about this hopefully at the end, but it makes a lot of use of fractals. So if you learn how to code fractals, you might be able to make, you know, better video games. All right. So specifically, so nature, so trees, lungs, the respiratory system, blood, so the circulatory system, and a lot more. These are just a few examples. I'll go into these in more detail in a bit. One silly example. So the other day I was eating some chicken soup, I believe, and I saw some bubbles floating, and I noticed there were like some medium bubbles, some small basically a ton of bubbles, and they were of different sizes. And maybe my mind was playing tricks on me, or maybe I was just thinking about fractals. I swear it looked like a fractal pattern where you just had these like infinitely decreasing in intricate bubbles all over the place. So next time you're eating some sort of soup with bubbles, just take a look. Maybe you can see a fractal pattern in there, or maybe you can tell me why I'm way off. All right. So here's the fun part. So, or sort of the fun part. So why do fractals appear in nature? I'm making a big deal about them like they're appearing, but let's get into it. So two reasons that I can come up with. They're simple and they're efficient. So what do I mean by simple? I mean simple in a very technical way. So let's think about it from like a DNA standpoint. So if you want to code something in DNA, you don't want it to take up like gigabytes of DNA code to create, let's say, a human. So you want to be very efficient. And luckily for us, fractals only require a few simple rules. So that makes them easy to code for in DNA, or basically just as a simple response to physical pressure. So to explain what I mean by simple, I think it's best to look at this diagram. So here we go. So what I'm attempting to draw here is a tree. So let's say we start out the way like I would draw this if you want to do this from scratch. You draw this part, and then you, let's say, halve it, and just angle it roughly 45 degrees to each side, and then take each one, halve it again, you keep halving it, and just add some leaves. All right, Now, I'm not an artist, but my point is that simple procedure generated something that looks a little bit like a tree. And now, if you think about it, this actually looks maybe reversed upside down, but this also looks similar to our circulatory system or a respiratory system. So in terms of simplicity, how can you come up with this minus the leaf part? You can just say grow 3 times your width and then split into 2. So let's say what this is like an inch, so this grew 3 inches, and then it's split into 2. Each one of these is a little thinner now, so it grows proportionally. So it keeps getting a little shorter and shorter and thinner, but there's more and more of them. So that's what I mean by it's very simple to code a fractal. It can be, not all fractals, but for like this complicated looking thing, all you have to do is specify basically 2 parameters. Grow 3 times your width and so then split into 2. Maybe an angle like at 45 degrees. So there's maybe a little more. But the point is, this is an infinitely intricate thing, and it only takes us a handful of parameters, a handful of numbers to generate this. All right. Efficient. Now this is really the cool one. Now here's 2 things. So fractals they allow you to increase your perimeter given an area constraint, or increase your surface area given a volume constraint. So think of this as 1D given a 2D or 2D given a 3D constraint, depending on your scenario. So for a lot of these examples, like the circulatory system that I've mentioned, we'll be referring to this star one, this surface area and volume case. So let me give you first an example of the first one. Now, I've attempted to draw a really terrible version of the Coke snowflake. Basically, you start off with an equilateral triangle, and then you erase the middle third of each side, and then you add on these points, and then you keep doing that infinitely. So here is just not a complete one, but like you could see, hopefully it gets more and more detailed, and you could find great illustrations online of how intricate this gets. The point I'm making is, as you add more and more iterations of these, the perimeter keeps growing, but the area is not growing. Like, in other words, it's never going to exceed this little part right here, but the perimeter will become infinite. Such shapes can become infinite, I should say. So that's the advantage of using fractals. So like, okay, so let's tie this back to actual biology. So let's think about trees or the circulatory or respiratory systems. The organism wants to keep growing with a minimal possible additional energy expenditure and increase in danger. So for a tree, if you want to get taller, let's say to get more sunlight, but you need to get narrower so that the tree doesn't break, and so that it's relatively easy to transport nutrients up that high against gravity. So there's competing pressures, right? So you want to get as tall as you can, but you can't quite grow infinitely tall. Now, so the reason to branch for a tree is you're getting more and more sunlight, the more area you're going to cut, the more volume rather you're going to be spread out over. So the same with the lungs and the blood. You know, we want our whatever system, circulatory, respiratory, it doesn't matter. We want the system to reach as far as possible throughout our body, and we want it, basically, that nutrient exchange to happen as quickly as possible. However, we don't want the systems to take up our entire body. So there's a kind of a constraint on how much energy and how much space they can take up. So I'll provide links. You guys should check out the links where this will be talked about more, such as in the Sapolsky lecture. But basically, let me give you guys a fact. So although, and I'm quoting this, although the volume of a pair of human lungs is only 4 to 6 liters, the surface area of the same pair of lungs is between 50 and 100 square meters. That's about the same area as a tennis court. So think about that. Your lungs are a pretty small volume, but the surface area is huge. And that's exactly what we would expect from these properties of fractals. And I want to actually tie this back to the previous page, which I forgot to mention. We talked about the 1D versus 2D shape and how this can be the continuous but nowhere differentiable. So the fact that it's sort of infinitely jaggedy allows us to, that was like the key property that we used to create in that video, to create a 1D shape that covered a 2D area. So, and that also relates to this property that we're talking about, efficiency here. So let's go back to the lungs and how basically our respiratory system. So can we, okay. So okay, let's go back here. So we can create a huge surface area with a relatively small volume, which is what I've just read, that quote about the lungs. So how is that done? Because if you're spreading out your surface and it's really intricate, it can be, let's say, relatively flat. So think of this tree right here. By getting smaller and smaller, you're gonna reach more and more of the regions. Now, why might we want this to be smaller? Because we want it to penetrate into all the parts of the body. So we don't want one huge like lung, because then it can't reach your fingers. It can't, you know, so it can't reach all the parts we need it to reach. So let's look at it this way. So our lungs are a certain size and can only hold a limited volume of oxygen. But then we have the bronchus, the bronchioles, the alveoli, all these other little structures, and they allow the nutrient exchange. So basically the shape of the lungs allows, because it has such a huge surface area, it can allow this exchange of oxygen to happen pretty quickly, because if it happened slowly, we would die. So I'll let you guys think about that. I'm afraid I made that a little convoluted, but basically we want something that's in a small volume but can quickly exchange nutrients and reach a lot of the parts of the body. So hopefully you could see why we would want to be sort of very intricate and get smaller and smaller, but at the same time not just be maybe all thin or all thick. So this is a natural thing to use, and combined with the simplicity, that might explain why they appear so often in nature. So like, hopefully this gave you an insight, the fact, and by the way, so true fractals can have an infinite perimeter and only a finite area. So as the Coke snowflake demonstrates, or as you can convince yourself if you look at other shapes. All right, so like I said, please explore more on these. Hopefully this just starts you thinking about why there's like circulatory respiratory systems that have fractal shapes. All right, activity ideas or idea. I'm a huge proponent of doing things through experience. So after looking through the resource links and getting some more knowledge and inspiration, I really recommend you guys either try drawing some or coding some, or better yet both, some of your own fractals. So how do you do that? I'll provide some links, but the basics are you have to come up with a few rules. So for example, you could think back to this tree. I'm gonna draw some sort of like two lines. I'm gonna have them branch at a certain angle and decrease by certain factors. So you're gonna have to figure out what are these parameters and what shapes you want to deal with. So like I said, play around with draw. You could start out with a pentagon. It doesn't have to be a tree shape. Your imagination is the limit. So any one of these, and keep in mind, video games, for all you gamers out there, you might have wondered, like, how do they create all of those trees in the background, or like these natural looking scenery? Like, do they actually have an artist draw each one of those things? And the answer is no. That would be way too time consuming. So there is some awesome code that's used for that, and I'll link that in the description. That also relates to something called Perlin noise. So I'll let you guys explore that in the description. And one other tip, if you're going to draw this or code, you probably already have realized this, but things aren't always perfect in nature. And also if it's super perfect, that's kind of one of the ways you know maybe it's not natural. So you might want to play around with adding some randomness or probability. So like in a real tree, they're not always curving, branching at exactly 45 degrees, right? Sometimes you get like an 60 degree bend. So play around with a little bit of randomness. Maybe add in some colors, some random colors, or some gradation of colors. That might make things really cool. So that's just to give you guys an idea. I'm sure you can find actual like specific tips on how to get this going online, but this will be a great exercise. All right. So one of my favorite parts, which is pretty much the end, and this is the significance. The significance application to your life, and aka why I love fractals, and hopefully something unique you can learn about fractals in this video. So yeah, you can find a ton of videos, read a lot of resources, and learn the basics, see all this cool stuff. I want to give you guys a little bit of like my own flavor, contribute something fairly unique, and I don't claim that nobody else has ever thought of these things, but that way you're not just like, oh, here's another video. I want to give you guys a little bit, something of my own take on it. All right, so I'm going to emphasize, so in a lot of these things, I'm going to emphasize the self-similarity aspect, basically, or related to the scale invariance, how there's similar things going on in different scales. So we can apply that to so many things. So for example, workout routines. So I know this is, educational videos, math, English, whatever, but hey, fitness is fair game because that involves education. So workout routines. Your heartbeats are actually not regular, they're fractal. So just as, parts of your body are already fractals, we might think like, can we apply this to actual workout routines? So, okay, for example, you might do different rep ranges. So if you're strength training, right, maybe you're always doing 3 repetitions or 5 repetitions because you want to grow stronger and you never work your low repetition ranges. So using the idea of fractals where kind of hitting things at different scales, maybe you do high reps and low reps and that helps smooth out, maybe prevents you from getting injured or helps you. I'm not going to get into the details of this, but if you're just someone that does a lot of repetitions of an exercise like push-ups, pull-ups, I don't know, squats, you may consider doing lower repetitions, maybe with more weight, maybe more resistance. Or if you're only doing low repetitions, try doing high repetitions. So basically mixing it up. And like, what is that? It's a bit of a stretch, but like it has to do with fractals, I would say, because you're thinking about things in different scales, not just like one thing. You're thinking of it holistically. All right. So, for example, also you could focus on high level wise in terms of different scales. Maybe you're just focused on your workout routine, but you have a lot of stress. You're not getting good sleep. You're not getting good nutrition. So, especially if you're not eating properly, you're not going to have the sort of the fitness goal results you would like to have. So that's one angle. Then there's the detailed angle. So we talked about the high level, on the low level, right? So like the medium level would be your actual routine. Low level wise, maybe when you're doing your routine, you're kind of zoned out. You're not really focused. So for those of you that are really into fitness, maybe you've heard of this concept of mind-muscle connection. And that just means that each repetition, you're focusing on feeling that muscle contract. So it's not just like counting numbers and like, let's say you're doing pull-ups and you're just like, oh, I want to get 7. It's like 1, 2, 3, 4, 5, 6, 7. They're all sloppy. So or as I like to say, 0, 0, 0, 0. But you're really focusing on quality rather than quantity, and you're focusing on that muscle working. All right, so that's just one example from workout. I know that I spend a lot of time on that, but it's not every fractal video you get fitness thrown in. All right. So, maybe this might be a little bit of a stretch, no pun intended, but I like this application to workouts. Then art. So, whether it's music, drawing, dance, whatever, similar principles apply at each scale. So whether it's the whole composition or a little part of it. So like with music, there might be the climax of the piece, right? But within each section, like the A section or the chorus or the bridge, there's maybe a tension and release pattern. So the point I'm making here, whatever applies on a small scale can also apply to the whole. So maybe if you're stuck on the whole, think about the small. If you're stuck on the small level, think about the basic on the whole, and they can reinforce each other. So the quality of the whole is going to reflect the quality of the details. So hopefully you're seeing this theme of thinking about different scales. There's clinical applications. Again, I would refer you to Professor Sapolsky's wonderful lecture. I'll put it in the description. There's something called Kalman syndrome, which is a mutation, and it has scale-free consequences. Scale-free is the same thing as scale invariant, similar to self-similarity. So what that means is there are mutations that occur at multiple scales across the body, whether it's the septum, like the nose, the heart. Anyway, I'll let you guys read more about that in the description. So that's useful in terms of clinical applications. Then your actual brain activity, or heart activity, if you're measuring the EEG, electroencephalogram, the printout, electronic printout, it's not a simple boop boop. There's a really complicated, intricate fractal shape to it. All right, let's say you want to write an essay or a paper, a story, a novel, a book, whatever. The same principles are going to apply whether you're at the paragraph level or writing a quick summary or the essay. So each paragraph of your essay is like a mini essay. So again, think to that Sierpinski triangle, Sierpinski gasket, and how you have triangles within triangles. Whatever principles you use to write a great paragraph, those apply on a larger scale to writing a great essay. Natural versus man-made. So let's say you want to decide whether the ocean is natural or is it nature? Did nature make it, or is it man-made? And this specific example of the ocean was pointed out again in that great 3 Blue 1 Brown user video. I'll link it in the description. The ocean has a fractal shape actually, and so if you look at trees, they're fractals. That's pretty natural. If you look at a table, such as this table right here, it's pretty flat, doesn't look very intricate and jaggedy, although these ridges might be a sort of fractal in nature. But anyway, so that tells you maybe this came from somewhere natural, but the flatness of it is probably man-made. All right, so that's pretty neat. And now here's the big one. Here's why I really love fractals. So this is going to be a series of them. So life and the universe. So all of life, and again, some of these are kind of my beliefs or my views. This is not so much right or wrong. I think this is a perspective or a way of looking at things. So I encourage you guys to think about all these things I'm going to say, but if you feel free to disagree, or if you don't find them helpful, then don't worry about it. So I believe all of life is a fractal, so literally everything. So from anything you can think of, whether like the principles of humans, whether it's animals, plant life, whether it's molecules, the whole universe is a fractal. So in physics, we have the fabric of space-time, and we keep finding particles on smaller and smaller levels. So we thought it was the atom. Then we found electrons, quarks. Some might say there's a limit, like the Planck constant, there's a limit to how low we can go, but I'll just leave it at that. So human experience. So all basically fractals show up. If you're sort of attentive and know where to look, they're just all over. Now this is the thing I want to focus your attention on, which is the life lessons. So I think you can learn something from the smallest things. So just like major life lessons and principles can propagate all the way down to the most minute details in daily life, you can also extract these major lessons the other way around by focusing on the most minute details and extracting the main principles. So whether you're cleaning your room or whether you're working on your next masterpiece, you can learn, if you're doing a sloppy job cleaning your room, that's going to, or vice versa. If you're doing a great job, maybe you can have an insight about something you're stuck on in your masterpiece. B, so all people are the same. So again, I don't mean this as a straw man caricature like we're clones or we need to think the same, but I mean that we're all interconnected and there's basically the same principles. Clean air, clean water, we all need social connections. At a fundamental level, if you think about how we go about our lives, it's almost like we're maybe different fractals, but the principles are similar. So we're sort of the same fractal. And again, I just want to throw this out there. I want to let you think about it, maybe find your own twist on it. Not to mention we're all made of stardust. All right, now this was kind of already part of A, but I'll mention it here. So how you do one thing is how you do everything. Everything is interrelated. So you can learn many of the same lessons at different scales and in different disciplines and areas. So if you're doing a lousy job cleaning your room, you're probably going to do a lousy job on your masterpiece or symphony or whatever it is you're writing. So another thing, So that's D. So these are all related. So I believe you can learn across disciplines. So whether you're rock climbing or doing math or going to the gym or reading a book, you might get an insight about something else. And that's because I think if you think about it in terms of fractals, a lot of things apply at these different scales. So again, I think fractals are a cool way of thinking about these things. And if you want to get philosophical about it, we can relate it to yin-yang and Taoism, the religion and belief system, and about boundary and balance. So, sometimes I'd like to get philosophical and with it, and for example, fractals, as well as chaos theory in general, straddle the boundary between randomness and very simple structure. So there's infinite intricacy, and I would say that's where, and by the way, the musician Yo-Yo Ma, the cellist, has made this point as well, that on the boundaries where a lot of the interesting, or periphery, is where a lot of the interesting thing happens, whether culturally, and I might make a separate video on that, but I just want to leave you guys with that thought on, just maybe think about how this might apply to philosophy. And also, if you go back to this yin-yang symbol, you have the dark that's part of the light and the light that's part of the dark. So you could think of it as many levels. So maybe the small is present in the large and the large is present in the small, if you go back to that Sierpinski triangle and think of it that way. But it could be anything. So whether it's feminine qualities, masculine qualities, you don't want someone that doesn't have a balance of, if they just only have masculine qualities and they're not in touch with their feminine side, or vice versa. If you're just all about darkness or all about light, and it's nice to have a balance, in anything. And fractals, I like that there's infinitely intricate at these various scales. So how does that relate to fractals? Well, one is the seed of the other. So in the small, we can find principles of the large, and in the large, we can find principles of the small. You can say, like, in the dark, we find principles of the light, and in the light, we find principles of the dark. So everything is interrelated. So that's how I kind of want to tie it into fractals. I'll let you guys think about that philosophy aspect a bit more. But, I just want to kind of put that on your radar and get you guys, that's all, just get you guys thinking about that. All right, and I'm going to wrap up with some foolishness. So go forth and explore. I hope this video at least threw out some things for you to think about. Some parts maybe weren't as successful, such as the long explanation and why it's efficient, but hopefully you got the gist of it. So yeah, go forth and explore further. Enjoy. I love getting your guys' questions, comments, insights. I love hearing from you guys, gals, and you guys are one of the reasons. You guys give me energy basically to make more of these videos. So please let me know, if you have anything you want to share with the rest of us. Let me zoom out on this foolishness over here. Don't even ask. That's just, I don't know, for foolishness' sake. All right, I'll see you guys in the next video.